Now we've experienced already various mechanisms to have power dissipation in power semiconductors. Power semiconductors are using silicon technology, most of them, also GaN technology or silicon carbide. Now, typically you start the thermal modeling with a die, with the chip, or also called the junction. So these are different names for the silicon, for the piece of semiconductor, rather small, few millimeters by a few millimeters typically, inside the package that are the actual semiconductor. Everything around it, the stuff that we mount and the stuff that we're soldering, is the packaging. Now, for modeling the thermal effects in the mechanical domain, we can define the temperature of that piece of semiconductor as a so-called junction. I'm using the Greek variable theta for representing the temperature here. Other people might use it the uppercase T, but I have reserved the uppercase T already for the period of a repeating signal. So for temperature, I'm using theta. As similar to the analogy between hydraulics and electronics, we can draw an electrical equivalent this time of the mechanical behavior of the device. A junction is hereby transferring into an electrical potential. So we have the junction temperature of a specific mechanical device, of a specific mechanical object, and that temperature would correspond to an electrical potential given in volts. Now, in the case of our TO220 packages, you have a big mechanical metal basis on the backside of the die, where the die is mounted for a good thermal conduction. And all the stuff being filled with white here, so you actually can look through it, seen from the top perspective, looking from the top at a TO220 device, is mold or plastic, which contains the silicon and keeps it mechanically in place. The thermally most interesting aspect is the temperature of the metal backside of the TO220 package, which has its own temperature, which is called the case temperature. And that transfers into an electrical potential of theta C, or the case temperature. Now, having two electrical potentials, we can draw a voltage from one to the other by subtracting one from the other. So there is a voltage difference in the electrical equivalent diagram, which corresponds to a temperature difference. And that temperature is based on the thermal resistance in between those points. The thermal resistivity corresponds to the ability of the material conducting the power losses from one point in the mechanical diagram to the next. The next thing you mechanically add to the stack is a very thin isolation layer. So I'm not defining the temperature of that isolation layer, but you want to have a very, very well thermally conducting, electrically isolating layer before you mount your device onto a heat sink. The heat sink is represented by the letter S for sink, and sometimes people abbreviate that also just as simply the sink. So you have to mount your device, your power device, on a sink. The temperature of that sink, of that heat sink, corresponds to an electrical potential in our electrical equivalent diagram. And again, we can draw a voltage difference, so a thermal difference here, which is given in either Kelvin or degree Celsius, depending on what units you prefer to use. And the transfer between them is the thermal resistance defined by the isolation and the capabilities of transferring heat through the mechanical stack from theta case to theta sink on the left-hand side. Now, finally, we have all the medium around our power device, which would typically be the air represented by the term ambient in this case, and assuming that it has a homogeneous temperature all the way around the device, which is the ambient temperature around the device. That ambient temperature is the starting point of our electrical potential and has an offset above absolute zero, which could be either 0 Kelvin or 0 degrees Celsius, depending on how you define it. In many use cases, this ambient temperature can be room temperature or 25 degrees Celsius, but most of the power electronic devices are also specified to operate at higher temperatures. In cases where the ambient is not air, it could be the vacuum out in space, or it could be even water or other liquids if the power electronics are submerged. Now, to finally model the power dissipation that we actually have in the junction, we can connect those junctions along the way, and to get the power out into the ambient, we are crossing each of those junctions, each of those potentials, thermal potentials, and that flow, as drawn by the red arrow here, is in the electrical diagram modeled as a current source, and its current goes through the series connection of all of those devices, and the electrical equivalent diagram closes the circuit by returning through the absolute zero to the negative potential of the DC current source. Now, to recapture the analogies that we used in this case, I have borrowed this table from Wikipedia. We have previously used the hydraulic terminology to connect it to electrical terms, and now we are using electrical terms to connect those to thermal equivalents. On a side note, there are also mechanical equivalents for the same modeling phenomenon. Now, to help us electrical engineers there understand thermodynamics a bit better, we focus on the two columns called electric and thermal here. The electrical charge lowercase q, measured in Coulomb, is represented in the thermal terminology by the heat with the uppercase letter Q, which is measured in Joule. The electrical potential, which we use typically in volts, is represented by a temperature in Kelvin. The uppercase letter T indicates Kelvin here. The Greek letter theta usually indicates that the author has used degrees Celsius as the unit. The electrical current in ampere can be converted into a thermal equivalent of a heat transfer rate, which is measured in joules per second, which by itself is equivalent to watts, as we have used in the previous slide. And finally, we have used Ohm's law by representing the thermal resistances through an electrical resistor. Connecting this to the previous slide, the thermal term of power dissipation in watts is equivalently represented by a current. The thermal absolute temperature theta is represented by an electrical potential. The difference of two temperatures is represented by a voltage, and the thermal resistance between two objects is called the electrical resistance in an electrical equivalent diagram. Now, using the example again of the power dissipation in the diode that we have previously calculated, we can use the assumption that the total amount of power dissipation in this diode is 6.2 watts. Going back to the datasheet of that diode, we can scroll down to the page number 2 and can find the mechanical characteristics of that package. Here we can find numbers for the maximum junction temperature range, in the operating range, and also in the storage range. Furthermore, we can find values for those thermal resistances that we've just looked into. In this case, they are given in degrees Celsius per watts, and we have the junction to case temperature and the junction to ambient temperature. The thermal resistance from junction to ambient assumes that the junction is directly cooled by the ambient temperature, so there is nothing else applied to the case other than the ambient material, and therefore no further cooling is attached to the device. The junction to case temperature is giving the so-called inner thermal resistance of the device only, and it can be used to calculate the thermal chain when attaching other cooling devices like heat sinks or having an isolation in between the device and the heat sink, and then using their thermal resistances to calculate the overall stack. Now, using these values from the datasheet, 50 Kelvin per watt and 3 Kelvin per watt, note I've changed the unit from degrees Celsius as it was in the datasheet to Kelvin, which is allowed as the relative temperature differences between Kelvin and degrees Celsius are the same, just on a different offset. Now, the first question is asking, how hot is the piece of semiconductor getting for those conditions if you don't apply any other cooling? And the second question assumes perfect cooling with a case to ambient temperature of 0 Kelvin per watts applied to the device and asks for the same temperature of the semiconductor inside the package. For the next exercise, a power semiconductor is assumed to have a total power dissipation of 6.5 watts. The maximum operating temperature of the chip is 175 degrees, and the thermal resistances are the same as we just have extracted from the datasheet and had in the last exercise. But this time the question is the other way around. The power electronics product is readily designed, and you're supposed to write the specification, the datasheet, the technical details for the end user. So which maximum ambient temperature, which surrounding temperature is the end user allowed to use the product in if there is no further cooling on the power semiconductors? Or if you could apply perfect cooling, how high would the maximum allowed ambient temperature be the user can use this converter in?